In this video, you're going to learn about how containers are implemented with a couple of Linux features, one of which is control groups and the other is namespaces. We're going to spend a bit more time on namespaces and do some demos because we have two separate videos dedicated to control groups, one for CPU and one for memory. If you remember back to our introduction to Docker video, we discussed the differences between virtual machines and containers. And virtual machines, we got isolation by the fact that an entire separate operating system was running on virtualized hardware. Where with containers, we're going to have to rely on some Linux features because all of the processes run on a single operating system. But now we need to understand how they're going to interact with each other in a safe way. So we now know what a container is. We know it's isolation from other containers, as well as resource limiting. It's time to demonstrate this. You're going to need access to a Linux machine to follow along because we're going to have a look at some of the internals. We're going to have a look at how we can inspect control groups and inspect namespaces, and that's only going to work on Linux. So now it's time to demonstrate namespaces in action. We're going to create a Docker container and see all of the new namespaces created. We're going to see one for process IDs, network, users, and mounts. The process ID namespace is what enables us to have our own process IDs inside our container. If we just have Java inside the container, it's going to get process ID 1, even though it's a real process running on the host, obviously not with process ID 1. Then we're going to have a look at network, and we'll see that inside our container, we'll just have a single network adapter as well as the loopback. But on the host, there'll be a whole host of them, one per container as well as the normal ones for the host network adapters. Having a good idea of an intuition for namespaces will give you a good understanding of how Kubernetes pods work later in the course. We'll use a few tools and some handy knowledge about the Linux file system to inspect namespaces. So if you've got it installed, you can use lsns, which stands for list namespaces. And we're going to do that before and after creating some containers. We can also inspect the process ID, the host process ID of our processes running inside containers. And then we can have a look in the proc file system to see what namespaces those processes are members of.
Right, I've just jumped into a regular Ubuntu Linux box. I've got two panes open. On one side, we'll run commands on the host, and the other will run some containers. So the first thing we can do is run lsns. That's going to tell us about the namespaces that exist on the host, and that's without any containers whatsoever. So let's do that. Okay, so we can see we've got one of each type. However, these aren't the only namespaces. If we were to do this with sudo so we can see everything, we can see a bunch more. These are actually created by systemd. They're nothing to do with Docker, but let's create our first Docker container and then see what namespaces are created. So we're inside a Docker container, flipping back over. If we run lsns, we don't see them, but if we run them with root, then we've got all our new ones. And it actually shows us which processes are inside when it's a single process. So we can see that the process 9202 is the bash process. But if we flip back to the container and run lsns, that same process is PID1. Then if we jump back to the host, we can have a look for 9202, and yep, there it is. It's a bash process. So that's our first sight of the process namespace. But why don't we have a bit more detailed look into that now? So I've run a Docker PS, I've got rid of the old container, and now I'm going to run a new one. So this time we're running a container on the left and we're going to do some host commands on the right. So I'm just going to run an Ubuntu container with the name test. And then let's have a look at the processes on the host first. So I've run a ps-e, which is going to show us all the processes, and there are a lot. We can also see the processes if we run top. Top is just a program which shows basic CPU, memory usage, etc. But if we jump back to the container, then we can only see a couple of processes. There's bash, which is the process we started inside the container, and then also there's ps, which is the PS that we just run. We can also start top. Seeing top side by side with a host, a container, and the container really demonstrates the difference here. We only see two processes on the left, but then we see all of the processes on the right. Now let's show you some more ways that you can map between processes in a container and processes on the host. So what we can run is docker inspect, and we can run that for any container, and it's going to give us lots of information about the running container. So if we scroll up, we'll eventually find process. Rather than running inspect like this and seeing every bit of information that Docker is willing to give you, you can pass in a format string. And the query for getting the process ID is .state.pid. So we can see that the bash process is 8852 on the host, but we saw that it was process 1 inside the container. We can find that process by running ps and piping it to grep, and there it is. But if I jump back inside the container on the left here, and I look for the process 8852, it just doesn't exist. Another fun thing we can do is we can run a kill on the host operating system for that process. So we're going to kill process 8852. We need to be sudo for that, and we can see the container on the left has been killed. And that's because we killed its root process. So next up, let's have a look at the network namespace. Here I've got the host on the left, and then I'm going to start some containers on the right. So we can run IP link show, and we can see the network adapters on this host machine. So I've got the loopback, which is low, and then I've got one real network adapter, which is the ENP0S3, and then finally we've got the Docker bridge network adapter. If we jump over and start a container, so from our favorite base image, which is Ubuntu latest, we'll jump into bash. We'll first actually have to install IP because the Ubuntu base image doesn't include it. So just run a quick apt update, then run apt install IP root 2. Yes, continue. And then we should be able to run the same command. Now these look similar, but they are different. We've got loopback, but we've got a different network interface, the second one there. And if we jump back to the host and run IP link show again, we can see we've got a new network interface. And that's because when you create a container, Docker creates a pair of them and links them up. Because the network adapters are separate in the container to the host, it means that by default, the containers are not going to be able to see your network adapters. In addition to that, it means that in our containers, we can open whatever port we like. And I'm going to demonstrate this with netcat. So netcat-L is listening on a port of a TCP on 4444. And then I'm going to try and do that in the container. Oh, looks like netcat isn't in the Ubuntu base image as well. So let's just quickly install that. Apt install netcat. Yep, let's install that. And then clear, and then yep, netcat-L 4444. Now, if I tried to listen on the same port twice on the host machine, the second one would fail. But we can actually see when we're in a container, both the host and the container can listen on port 4444, which is great.
Now that we've had a good look at namespaces, let's switch to control groups. So just like namespaces, each of the containers that you create with Docker will get put in a set of control groups just for that container. These will limit the amount of CPU it can use and limit the amount of memory. When we've been running Docker run without any additional parameters, there's actually no limits. But let's see the effect of adding limits now.
So let's start ourselves a container so we can have a look at the control groups that are created for it. Just a regular Ubuntu latest with the bash command. So one tool that's quite handy is systemd cgroup top. So there's all sorts of C groups running on this machine. The only ones we're going to care about though are the ones underneath Docker. And we can see the Docker one there using very little CPU. So what is that big number and letter thing? Well, that's the ID of the container. So the C groups that Docker contains will be named after the container ID. So you can always match them up. Now we can see once we've deleted the container, or by exiting it, it's gone from cgroup top. Well, that container wasn't doing anything, so it wasn't very interesting to look at in cgroup top. But let's start using some CPU inside our container. So we can do that just by writing a while loop, which is just going to keep printing echo world. And this will use a reasonable amount of CPU in that loop because it's just a hot loop. So let's open up systemd cgroup top again. And there we have it. Our container is using about a third of a CPU just to keep printing cat or a lot. A Docker specific command you can use to see this stuff as well as Docker stats. So here's our container and we can see the same numbers. All of these numbers come from the same place. You can access the information about C groups on the Linux file system. So let's have a look at that next. So again, this requires us to be on Linux. We wouldn't be able to do something like this on a Mac. So let's just first kill our container. I think we've printed cat quite enough times. And let's go to the sysfs C group. So for each type of C group, there's a folder. Let's have a look inside the CPU one. And there's all sorts of files here with various statistics. And C groups are hierarchical. So the same structure that we saw in C group top is represented on the file system. So we can jump into Docker and then into the specific containers. One really useful file that we're going to use throughout this course is cpu.stat. That includes a counter for when your container is throttled, which can easily happen when running multi-threaded applications inside a Docker container once you start putting CPU limits on it. So for instance, the other stat file we've got is CPU accounting.usage. And if we start our cat printing back up and we keep looking at the contents there, we can see it keeps going up. So we haven't given any limits to our container yet. So the next step is to add limits and see how the C group makes the container behave differently. So let's open Docker stats back up, flip over to the other side, kill the container, and then execute it again. But this time we're going to use the -- CPUs flag. And we're going to set it to 0.1, so 10% of a CPU. There's quite a few different CPU related flags for Docker and for control groups, and we're going to go through them all in the next video. So we'll kick that back up, and I think we've probably printed enough cats for this video, so let's print dog instead. Off it goes. We can validate that over there in Docker stats, we've got a similar CPU usage. No, we don't. We only have 10% CPU, whereas before we were using up 30 to 40% of CPU just printing something to the screen. We can show the same stat in cgroup top. You can see that Docker container has 9.9%. Now that we've added a CPU limit to our container, we can pop back into the cgroup file system, pop into the directory of that container, and we can have a look at the throttling. So before, when it was unthrottled, it was using 35% CPU, whereas now it's only using 10%. We can stick a watch on catting of cpu.stat, which will refresh every 2 seconds, and you can see that the throttling is going up and up and up. Now, we don't really mind that we're throttling and printing out dog, but if this was your Java application, this would actually be introducing latency and delays to your Java application. So it's super important to understand how this can happen with different settings and how to avoid it.